Hey everyone, welcome to episode 3. We're going to talk about load devices, or at least we're going to start talking about load devices. These devices are the part of the circuit that actually does some useful work. So with a variety of circuits out there in order to accomplish all their tasks, I guess you can kind of see that there wouldn't be really any way to cover those in any sort of video that could last under hours or days. And you don't want to put up with that, so we'll begin breaking it down into just little chunks. So the first part that we're going to talk about today is just what makes a load device, what are some basic categories of load devices, and depending on what your interest area or your particular field of study is, some areas of these load devices might be of a little bit more particular interest to you. So later on then we can split up and talk about those individual categories, and then you can pick and choose which of the videos and episodes might be a little bit more relevant to what you're interested in. Now, since I like electronics, I tend to be sort of interested in everything that has to do with electronics. So that means I don't necessarily have an in-depth knowledge of every single category and every single new article that comes out about some advanced research on some new topic. I have to really kind of pick and choose what areas I focus on the most. So I usually tend to stay with those areas where I can build a circuit and I can experiment with it and help me learn a little bit better, which means that most of the parts and pieces that I use are fairly low cost, usually fairly large. Some of those really tiny devices, they call them surface mount devices on a circuit board. I really don't get into those very much because it's very difficult to experiment and kind of play around with those and sometimes risk breaking some things, but just being safe the whole time. Fortunately, with most of the circuits that have very small voltages, these little microcontrollers and microprocessors, they keep things very safe. The thing that I'm most worried about in those cases is damaging the circuitry. So it still pays, sometimes pays pretty greatly, to pay attention to being safe, but with the small devices and small voltages, we don't have to worry as much about harming ourselves. So they make great platforms to be able to show and demonstrate and experiment with and make sure that everything's working. So these different categories of load devices, it doesn't matter what area we're talking about, whether it's industrial or microprocessors or nanotechnology. The purpose of a load device is to convert the energy of the electrons, which they call electrical energy in the circuit. We want to convert that energy into something else. I know that's pretty vague, but the different purposes of circuits can convert things into, like a motor is a really common example of a load in a circuit. So we're converting electrical energy into mechanical energy. Light bulbs, another extremely common example of a load device, where we're converting it into light energy, and most of the time heat energy as well. Sometimes it's motion, not just rotary motion like in a motor, but sometimes we want to be able to move things forward and backward. A lot of times that's accomplished through what we call a solenoid. A solenoid is, well, we'll talk about exact mechanics of that one. Solenoids and motors have some extra quirks in the way that they work by generating some magnetic field properties, but it's a little bit more complicated. So we'll discuss it in depth, but it's a load device that's extremely common for moving in a linear fashion. So we'll start with the small stuff. The little tiny load devices are most easily represented with a device in electronics that we refer to as a resistor. Because a resistor, just like its name sounds, it resists the flow of electricity. So while voltage is trying to push electricity through the conductors in our circuit, we already talked about this power supply that supplies that voltage or that push, that pressure that tries to drive electrons. The conductors give us a path for the electrons to flow. Without a path, it would just be a dead end. The voltage would be present, but there would be no motion. But we finally have to have this third extremely important piece in a circuit, that is the resistor, to both convert the energy from electricity into something useful, light, heat, motion, etc., but it also serves to slow down the electrons. In a pure conductor, a really good conductor, we can think about that like a water pipe that's huge. A giant water pipe really has no limit to the amount of water you can throw through it. So if we have a gigantic pump, a huge source of water, and a huge pipe for that water to run through, you can expect a ton of water to rush through the pipe. Now, if we have a very small pipe and a massive source of water, we can probably expect less water is going to flow through that pipe. So the resistor acts kind of like the size of the pipe, or a better way to think about it is, it's like the friction in the pipe. So if a pipe is small, it has a lot of friction. A wire that's small also has a lot of friction. So in that way, we can think about them fairly similarly. But sometimes these other devices, these load devices, also have some sort of friction. And just like friction creates heat, which is a conversion of energy, a load device will also have some sort of electrical friction, which is a conversion of energy. Now, there's actually with heat in particular, that's a good hint that something has some sort of friction or resistance. There are very few devices that can convert energy without heating up. In fact, there really aren't any. Heat is, unless it's intentional, like your heater in your house, obviously that's an intentional source of heat, your oven, stove, heat lamps, obviously those we have to have heat out of, that's the whole purpose of them. But most other things, our purpose is to get something else out of it, like a light bulb, a motor. Our purpose is to get something to move or to light up. We don't need heat. Heat is a byproduct, and in most cases, it's a waste of energy. If a motor is heating up, just like your car engine, it heats up, but really doesn't do anything useful. And well, okay, it runs the heater in your car, so I guess on a cold morning that's useful. But in the middle of summer, having that extra heat that's sent off by the car engine is a ton of waste. Because not only do we have to just get rid of it, we don't want to heat up, it's the middle of summer, so we got to get rid of the heat. But that means we also have to run water pumps and other things to cool off the engine, so we got to throw in more energy just to get rid of the extra energy. Heat is a big problem, not just in mechanical systems like that, but also in electronics. Heat is a dead giveaway that something is being some energy is being converted, and therefore there is a resistance or a friction for the electrical energy at that point in the circuit. Every load device is going to have some sort of heat, and even other devices that aren't necessarily loads, like when we talked about conductors, we said you need to make sure that you tighten down all the conduction connection points, that there's no corrosion being built up, because if there is, that means that there's going to be some heat given off, and that's, again, it's a sign that there's some sort of friction. So it's kind of behaving a little bit like a load, but we didn't want that load in the circuit. We want to save all of the electrical energy for the thing that's doing work. So what can we produce with a circuit? Like I said, those most common ones. We can produce light, heat, motion, and another one is sound. We want to be able to drive speakers. That's a really common load device. Now there's others that are a little bit specialized, and there's certainly other load devices that convert electrical energy into something else, but really those are the main ones that we see all the time. Light, heat, motion, and sound. So we'll be looking a lot over the next bunch of videos about how to use every one of those properties and turn our energy from the battery or from the voltage source through the conductors into some sort of usable quantity. So we'll start with the small stuff first. Let's look at an example of those. So light is the first one. Now we have incandescent lights in a circuit, but honestly incandescent lights are sort of falling out of popularity. And they're still really inexpensive and super simple to use because we just put electricity into them, either direction, direct current, alternating current, and they convert energy into light. It's really simple. But the problem is they also convert a lot of that energy into heat. In fact, it's pretty common to be able to identify the difference between an incandescent and an LED, like a light bulb in a house or any other application, because if you hold it or put your hand over it, you're going to feel heat coming off of an incandescent light. You're going to feel very little, if any, heat coming off of an LED. And so LEDs then, if most of the energy is not going into heat, it's going into light, that means that they're going to consume less energy. And so they're going to cost less to run. But it's always kind of a fight because they cost more to install, even though they save money. So you got to make the decision up front. Are we going to use LEDs or are we going to use incandescents? Now, sometimes we're kind of limited in that, like we're running off of a battery. Well, it doesn't really matter how much electricity costs then. That battery may simply not be able to run an incandescent light. So that's why kids' toys, small battery-powered devices, 100% of the time they run with LEDs, not incandescent lights. Just because the battery can't supply the amount of energy required to run it. So for the sake of a couple extra pennies, LED versus incandescent, of course we'll go with the LEDs. They're also much smaller. The color of an LED is based on the material, the semiconductor material that's used to design it. Rather than with most lights, the color of the light is based on the color of the bulb around it. So if you wrap it in green plastic, you'll get a green light. If you wrap it in red plastic, you get a red light. Like your brake lights in your car, they're only brake lights or turn signals. They're only red or amber because of the color of the plastic around it. Now, when we switch to LEDs, if it's a brake light, a red LED, the color is going to be there regardless of whether the case over it is red or clear. You can put a clear lens over it and red light still comes out because of the material, not because of the cover. So here's a couple of examples of what a typical LED would look like. This is what most of them look like down at the surface. Now, just like I mentioned before, tiny little devices is called surface mount, or sometimes an acronym for that you'll see is SMT or SMD, surface mount devices and surface mount technology. They're really common. Here's an example of a board. Look closely at that board. Lots of tiny little devices. In fact, there's even a little processor in there. I turn it over and look at the back, and there's some where I have to hold it up to my face to be able to see some of the parts in there. Let me see if I can get you some good angles there. Those are tiny devices. Obviously, I'm not going to go trying to experiment with devices that are that small. I can't even hook wires to that. That's going to have to require some specialized equipment just to connect it to the board. So for those, I'm going to stick with the parts that are big enough for me to bend the wires and stick them into battery terminals or breadboard to be able to connect. Make it easy. Those surface mount devices are cheap. They're mass produced, so they're very easy for a machine to install if you're going to be selling thousands of a board. But if you're just experimenting, stick with the other stuff. Instead of surface mount, we call these through-hole. If you do a lot of electrical experimenting, through-hole devices are the ones that we can connect to just about anything we want. These LEDs are called 5mm LEDs. There's also some that are a little bit smaller. They're 3mm LEDs, and some that can be much bigger, even up to 10mm LEDs. But this is the typical size and shape. For these LEDs, if you look really closely at a brand new LED, one of the wires will be longer than the other. Also, if you look very closely at the LED, one of the sides of the LED, the little shoulder at the base, it sticks out. The other side does not stick out. That indicates the flat side is what they call the ground side, the side that's going to be pointing closer to the negative side on the battery. The long wire, the one without the flattened off side, the long wire is the side that's going to point more towards the positive side of the battery. Now they have names that go with them, anode and cathode, but honestly I prefer thinking about it in terms of the plus and minus of the battery because that has a direct printout right on the power supply or the battery. So it's a little bit easier to think about things in terms of plus and minus of batteries, even though maybe it's a little less technically correct. Along with LEDs, so that's our light, let's think about heat. Now, heat's kind of a tougher one to think about, a device that creates heat, because most of the time the devices themselves that create resistance, we have devices in electronics that are called resistors because they simply resist electricity. They don't do anything useful on their own. They're made for one of two purposes, and one is getting the electricity to behave the way we want, just conditioning the electrical signal, externally changing and limiting the amount of current, or we can use them to create heat. Resistors create heat by converting the electrical energy through the electrical friction into heat that just radiates off of it. In fact, the bigger the resistor, the more heat it's willing to withstand before it burns up. A lot of times that smell of burned electronics, if you've worked with electronics, you've probably heard the joke about the magic smoke. Electricity and electronics always works because the magic smoke stays inside of it. If the magic smoke comes out, then that's what causes the device to fail. Well, the magic smoke is really just components, usually resistors or capacitors burning up, and they both have very distinct smells to them. But if we've rated the resistor properly, the size of the resistor is designed to withstand the amount of energy being sent through it, then it converts that into heat and can protect the other devices, or if it's a heater, it simply creates heat. And that's really all a heater is just resistive elements that are designed to get really, really hot without burning up. Your wall heaters, baseboard heaters, hair dryers, heat guns, industrial heater devices, all of those are simply resistors that are sized so that electricity heats them up like crazy, but they don't burn up. Some resistors can be much smaller than that, but Some are even bigger and made out of lots of different kinds of material. Okay, so that's light and heat. Motion is another one. Motors come in all shapes and sizes. Here's an example of a little hobby motor. This one usually there's a variety of voltages that these little tiny motors can run on, common down to 3 volts all the way up to sometimes 12 or even higher. They spin extremely fast, but they're pretty weak. So if you plan on using them for anything useful, then sometimes you got to install a little gear reduction system on them to make it go slower, but with a little more force. With these ones, you can often run them off of even a small battery. But as soon as you touch your finger to it, it comes to a stop. Extremely fast, not real tough. So we have to design those, but since they're so fast, we can install any gear system we want on it, and it works pretty well. Speakers are the last form of common energy conversion into another form. A speaker is simply a little panel that moves up and down, vibrates, and pushes on air molecules. And if it buzzes, if it pushes on those air molecules at just the right frequency, that's interpreted as a sound. That's exactly what a speaker is. You send electricity into it at a particular frequency, it vibrates that speaker element up and down, and as it vibrates, it pushes on the air, and that air, then the waves of one air molecule hitting another air molecule, hitting another air molecule, finally reaches your ear, and you hear sound. It's not really as complicated of a device as most low devices aren't really as complicated as they might seem when we think about how electronics works. Sometimes it's just so intimidating to think about how complex these circuits are, the things controlling them. We go, man, this low device has got to be more complicated than this. Most of the time, no, it's really not. They're pretty simple. We just have to come up with some cool tricks on how to make them behave properly. So that's the quick introduction to the different variety of load devices for the really small stuff. Now let's look at load devices for the really big stuff, the industrial applications. There's a couple of main categories. There's the devices that are meant to control other devices, and they're considered a load device because we have to supply electricity in a circuit in order to get them to activate. But their whole job is going to be to get the dangerous voltage levels to a place where the operator doesn't have to touch that dangerous voltage level at all. The operator can push the go button with only a tiny little voltage. That tiny little voltage activates a load device. That load device then allows the huge voltage to run the huge devices like big, huge motors and heaters like we were talking about, but these heaters can be like 240 volt, multi-thousand watt heaters. So they're meant, these load devices are often meant to keep the operator safe and allow the bigger voltage to be off in a different place to allow the large current to flow to make the huge devices run. So a couple of examples of those kind of things would be the relay. The electromechanical relay is just a really common, kind of a classic go-to industrial control device because it has not only the load, which is the coil is what we have to send electricity into, and its job is to create the motion of little copper switches clicking over into another position. So in one position, they're open. We apply energy, they close. The coil also has an extra, it works on a coil that creates an electromagnet. I was talking about solenoids, motors, relays. Those are going to get a whole separate discussion in themselves because they work on a principle called induction. They do create resistance to electrical flow, so they do restrict the amount of current that's being flown through the circuit, and that's good. But they also create what's called induction, and the effects of induction in the circuit can sometimes be pretty harmful. So we've come up with some ways to be able to protect against that. But that's another discussion for later on. At least what we need to know for these relay load devices is that the coil of the relay is the load that we want to turn on and off at the appropriate time. Another device that's kind of like a relay, just a little bit bigger, is referred to as a contactor. Sometimes you'll hear these referred to as motor starters, but a motor contactor is only different from a motor starter because a motor starter has some extra pieces that they call an overload, a thermal or magnetic overload that'll automatically stop the circuit if too much current is trying to go to the motors. In these cases, we're talking about motors that don't run off of 3 volts or 6 volts or 12 volts and buzz really fast. We're talking huge motors that can be 50, 75, 100 horsepower motors that are just absolutely massive. The scale of industrial equipment is often something that people who only work with hobby electronics just can't even begin to imagine. If you ever get a chance to tour an industrial facility that's automated or has machinery working in it, take up that chance. It's going to be some stuff that'll really impress you. It's amazing to see that working, even if you don't understand how it works or all the ins and outs of the control. That's okay. Just be amazed at the size of that equipment in there. Just the devices needed to get that stuff running and to maintain it and to control it is just pretty incredible. So that kind of is the resistive load device, and the motion is involved there, because both of those, their whole job is to make a switch move. Well, switch moving is motion. It's not rotary motion like a motor, but it is a switching action. Solenoids, which can be air valves, or like your starter in your car has a solenoid, which is a little plunger that makes a tiny little gear mesh in with a huge gear that starts the engine going. Now, if it wasn't for that plunger action, that gear would never be able to mesh with the other gear. Have you ever turned your key on while your car is already running and it just makes that horrible grinding noise? That's a gear from a plunger that's trying to move forward and mesh with another huge gear, but that huge gear is already moving. And so that noise is that gear just trying to, that's a bad noise. When you hear that noise, let go of the key, because that can really do some damage to those two little gear teeth that are trying to mesh. So starters have a rotary motion, it's a motor, a starter motor, but it also has a starter solenoid that engages the gear. Now, light is another really fun one in industrial electronics. And lights can come sometimes inside little push buttons. So sometimes you'll push a button and it'll light up. That means there's a light inside of it. And sometimes lights, if you've ever seen pictures of machinery or worked around machinery, these stacking lights, these tiered stack lights, are also really common. They can be both incandescent or LED. Both are widely available options. If they're LED, then sometimes you'll see like 4 clear tiers on it. The plastic will be clear, but different colors will come out. That means it's an LED. LEDs consume a lot less electricity than incandescent lights do, so they're an ideal choice when you're running tens, hundreds, thousands, even in a huge facility of these lights simultaneously. If you can switch out incandescents with LEDs and save like 60 or 70% of the total power usage for your lights, that can add up to a pretty significant amount. Now, another one, let me walk here and grab this. Another load device that we see commonly is motors. Motors deserve a lot of discussion all in themselves. This is just a small example of a 3-phase motor. These 3-phase electrical motors can be anywhere from fractions of horsepower. We've seen some down in like 0.1 or 0.2 horsepower. This tiny little 1/20th of a horsepower, even just tiny little motors, all the way up to huge 7,500 horsepower motors or even bigger. There's some massive variety in what kind of motors we see. And there's DC motors, AC motors, single phase and 3-phase motors, brushless motors, servo motors, just all kinds of varieties. And a lot of them actually work on a lot of the same principles. So rather than trying to discuss all those right now, we'll just leave that for another time. We'll have more videos just on motors. They're a fascinating subject. But we see them all the time. They run so many things that have motion, everything from, if you have a blender in your house, most likely, yeah, that's running on an electric motor. Anything that spins, if you got a battery-powered kid's toy, there's probably some electric motors in there. Simple little devices, but they're everywhere. Now, a third category of load devices, it's not really necessarily reserved for the small hobby stuff and the little electronics or the huge industrial stuff, and it's not what we could consider a device in itself, like a motor. That's a device. A light bulb, that's a device. It's a single device that we can think about as turning on and off. But sometimes a load will be another form of processor or another, what we might call controller, inside of a system that deals with information handling. So let's say we need when we push a push button, we want a series of things to happen. We want 6 or 7 things to happen. We push the go button, and as soon as you push the button, it begins starting this one thing, and then 3 seconds later it starts this other thing, and then 3 seconds later it fires off these other 3 things in a row. It's a pretty complicated sequence of instructions to happen. So instead of trying to manually wire all those things up with the right little timer circuits, what if we could have a controller that could simply do all that stuff with a pre-program? And that's what we try to get to, no matter whether we're dealing with little hobby stuff. The microcontroller industry is all about trying to design programs that can turn complicated series of instructions into much more simple programs that can be adjusted and tweaked with just a couple of clicks and then press download instead of rewiring the entire system. So sometimes things will look like this. This is a little stepper drive system for driving a stepper motor, which we'll talk about motors later, but it has all kinds of extra circuitry inside that makes the motors more efficient, more precise. They're really common for driving CNC machines. It's like CNC lasers, mills, engravers, things like that. Stepper drive systems are a really common form of driving those kind of motors. This is a servo drive. On the outside, they really don't look like much. If we were to open up this case inside, it really wouldn't look that obvious. You wouldn't know what you're looking at because you just see this green circuit board with thousands of components soldered to the front of it. So all that stuff inside, we can consider as a load device. You push the go button and this device, this controller does some things. Well, if it's doing some things, isn't that what we said a load device is all about? Turning your electrical energy in your circuit into something else. It's just a little bit more complicated because we would say the load device from that push button is now the controller, but now the controller is driving a whole bunch of other load devices of its own. So the controller is just kind of this box in between all of the stuff that you push and pull and levers and sensors, and all of your final devices like the motors and lights and relays. The controller is that thing in the middle that figures out what to do with all of the inputs and then figures out how to make the output stuff do what we want it to do. But since we drive that little controller with the buttons, that means that it is the load device. It completes a circuit by allowing us to convert that energy into, instead of light, heat, motion, energy, it actually converts it into information, which is a little bit harder for people to wrap their heads around just thinking about pure electronics. But if we could turn it into information that a computer is able to read, suddenly we've put a digital controller into the middle of the system. But every digital controller that you can hook a sensor or a push button to immediately becomes a load device. A pretty popular one in industry, if you've ever been around industry, you've probably heard the term programmable logic control, or PLC. They come in all shapes and sizes. Here's just a really simple example of a PLC. Just a bank of screw terminals in one place and a bank of screw terminals in another place. They really aren't a whole lot to look at, but the purpose of it is we connect all of our push buttons and sensors, making this act as a variety of little load devices inside. Each one is completing a circuit and checking to see whether we've pushed a button or whether a sensor's been tripped or whether a selector switch has been turned and rotated. All those kind of things are input information into it. So that means now that we're allowing the programmable logic control to turn the electrical energy into information. The program inside of it then converts that information into decisions. That logical decisions drive all of the stuff that's connected to the outputs. So for that reason, we can program it. So we call it a programmable logic because it makes decisions based on logic controller. Some small devices, this is a variation, it's called an Intel Galileo. It's a little variation of a really popular programming platform called the Arduino. If you've been into the hobby world at all, you've probably heard tons of references to that. I have so many of those myself, lots of different projects running on those, lots of fun, but they really are exactly the same idea as that programmable logic control. We send information into it through the form of push buttons or sensors, the ability to measure the light amount in the room or the temperature outside, and it converts that into some other sort of action. So for that reason, we can think about it as a load device. And that's really important because making connections to these controllers can be a very confusing process. They're complicated. So trying to figure out what to do with it is a little bit of a daunting task. But if we just think back to the basics of a circuit and we go, okay, I got my power supply, this is the battery driving the thing. I got the conductors, good. I now need a load device. Okay, I have a controller. How do I make the controller act like the load device to complete the circuit? If we don't try thinking about it as a whole new complicated component, just go back to the basics and think about it as a load device, we can make our connections. Now we'll also have to think about it as a source, a power supply for the other things, like if it's trying to turn on a light, the controller becomes the power source for the light, but now we just think about that as a separate circuit. We don't overcomplicate it. Overcomplicating is the easiest way to fall behind in electronics. Because if we think about all the stuff you can do with electronics, you get confused really fast. So instead we stick with the basics. Every circuit needs three things: power source, conductors, load, and probably will contain, probably 99% of the time, will also contain control devices. So necessary is 3 of them, 4 of them is most likely. And if we can boil every circuit that we connect down to those 4 devices, not only can you construct it more easily, but you can troubleshoot it if it breaks more easily, and being able to trace it and verify it before you flip that power switch and make sure everything is working is much easier, because you can have a project that has 1,000 wires in it, and if you just bring it back to a simple path of electricity from a power supply through the conductors to the load, including any control devices, you can verify the first circuit. Then you can verify the second, and then the third, and then the fourth. And instead of thinking about this massive assembly as hundreds and thousands of wires, you think about it as little tiny sections of a power supply, conductors, the load device, and any appropriate control devices, and bring it back to the simple stuff. Electronics is complicated. I'm not saying that it's simple, I'm just saying that if we overcomplicate it, it's going to be terrible. So let's not overcomplicate it, let's keep it simple. And as we walk through the next series of videos, you'll certainly see a lot of applications of electronics. This is really just a survey at first here. This is just a taste of some of the things. We'll actually show a lot of these things in action and how they fit into the circuit, both from the small scale level with little digital circuits and processors and little speakers and motors and LEDs, all the way up to some of the big 3-phase control using the industrial control devices. We'll also look at microprocessors and the programmable logic controls that provide those logical decisions, no matter whether it's operating at kind of the hobby, tiny, little small voltage level or the big industrial level. The operating principles behind the devices are exactly the same. They just design them for slightly different conditions. So I hope you've enjoyed these first 3 so far. The next one will give a survey of control devices. That'll be the next step in the whole thing. And again, as always, if you have any questions or comments, or there's something particularly you want to see, please just let me know, and I'd be happy to address that. I hope you enjoy the study of electronics as much as I do. And if you have any questions or want to learn more about this kind of stuff, I can certainly point you to some awesome resources and some places to find more information about it. As always, have a great day and go build some cool stuff. See you later.